Okay, so I guess I'll just start then. Herein we'll also be covering stats. How long will the live stream be? Mine will be short, probably only 30 minutes, maybe an hour max. But the other ones can take longer, depending on, just, I mean, like stats and calc and all that other stuff can take longer. Afterwards, we'll also be covering options. I can be doing uh, sorry, I'll be doing calculus here, and I think we'll be doing discrete. So that's how it's all going to work. Um, okay, so I'm going to start with polynomial functions. So we define a polynomial function or kind of the general definition that I don't know if you need to know this, but certainly in the syllabus is kind of this. It's the sum, or sorry, it's just basically this. So some function is equal to this. So essentially that uh, it's any kind of function which is just uh, powers of x greater than 0 essentially. Um, so this could be just some with some variable sorry with some coefficient in front of it. So x to the 1 plus a2 x squared all the way to the nth one, and a polynomial takes some form of that. Now, the important thing with polynomials is there are kind of a few things you need to know about them. One of them is the one of them is polynomial division and factoring. Then there's also the factor remainder theorem, as well as sum and products of the polynomial roots. So I'm going to start with polynomial long division. So just like normal long division, polynomials can be divided. So for example, if you have a polynomial 3x, 3x to the fourth plus 3x cubed minus 8x squared plus 9x minus 7, this can be this can be divided by x minus 1 to get you 3x cubed plus 6x squared minus 2x plus 7. Now, to do that, it's same as normal long division essentially, but you just work with polynomials and variables instead. So I'll run through a quick example here. If we have that same one, right? Minus 8x squared plus 9x. Now you need to know this because some problems that they can throw you in the exam is they'll give you, for example, a cubic equation, and they'll tell you that one of the roots is say -1, and and they'll ask you for the other two. So what you need to do is you need to factor x plus 1 out of the cubic that they give you, and then you'll get a quadratic equation, which then you can apply the quadratic formula. So anyways, if we do this, we can see that if we multiply this by 3x, if we multiply this by 3x cubed, then we get 3x to the fourth minus 3x cubed, and then this gets us to 6x cubed minus 8x squared plus 9x minus 7. Then if we multiply this again by 6x squared, then we can get minus 6x squared, x cubed minus 6x squared, so this is minus on this whole thing, sorry. So then again, just like normal long division, this gets us, so it's 0, and then we move on to minus 2x squared plus 9x minus 7. And again, we do the same thing. We multiply that thing by minus 2x, so we get minus 2x squared minus 2x, and then it all factors down to this last one, which is 7x minus 7. So we can clearly see that if we do a plus 7 here, and there you go, you've just factorized this polynomial. Boom, 0. Okay, and essentially that's how you do it. It's not too complicated. If you have any actual problems that you want me to run through, send them over. I can do them. It's not too difficult. Now, you can occasionally get a remainder. and this is important because of the thing that we're going to talk about next. So, for example, actually, I guess one such kind of factor that you might want to know is the difference at sum of two cubes. So essentially, if you have some, I guess I can write it generally, a plus b, or sorry, a cubed minus b cubed. So this could be, for example, x cubed minus 1. Then what you can do is you can factor this into x minus 1, and then x squared plus x plus 1. Or sorry, not. Sorry, this should be a's and b's. A minus b, and then a squared minus ab, plus ab plus b squared. And same for the sum. Again, these you can find essentially by long division. It's just the opposite form. So these are good to know. They do sometimes come up, but I don't think too much. Anyways, moving on. So, like I said, these come into play because there are two theorems that you need to know about, which is the factor-remainder theorem, or sorry, the factor theorem and the remainder theorem. Yes, the revision session will be uploaded to YouTube after it's done. So the factor theorem and the remainder theorem. I'm just gonna write that. Okay. So so the factor theorem states that a polynomial function, p of x, has the factor x minus c if p of c is equal to 0. And that's the factor theorem. You need to know this. Occasionally a question they can throw up against you is essentially they'll give you or they'll tell you that this is 0 at this point, and then they basically want you to plug it in, and you get another equation out of that which you solve. I can't think of off the top of my head. This you do need to memorize, unfortunately. But although if you think about it a little bit, then it kind of makes sense, because then if x equals c, you get c minus c, which is 0. So of course it has to be. The other one then is the remainder theorem. The remainder theorem is such that if you have, if a polynomial p of x is divided by x minus c, then the remainder the remainder value is p of c. And this is kind of, it's almost like or I guess the factor theorem is almost like they're kind of similar. But again, this is something you need to remember, because they do occasionally need you to show this, and this is sometimes easier than doing the actual polynomial factorization or long division. So these two are very important to remember. Yes, so let's move on, I guess, unless you guys have any specific questions about this. It's all very straightforward stuff. Okay, so I guess if not, I'll give it a few seconds because of the stream delay. Okay, I see no questions or anything, so I'm going to move on to the sum and products of polynomial roots. So essentially, we can start off with an example, which is very simply that, let's take x minus 4 times x plus 3. when did you do statistics? Hiran will be doing statistics, I believe, next after he covers vectors and induction. We've split this up between 3 helpers, so it'll be 3 different streams basically, and then we'll do options after all of that. We've already covered SL statistics, so the only statistics that we'll be doing is the HL statistics. Anyways, so then we can see that this is equal to x squared minus x minus 12, right? So now we can see that the sum of the sum of the what am I thinking? Oops. The sum of the roots is minus 4 plus 3, and that's just equal to 1, right? And the product is minus 4 times 3, which is equal to minus 12. Now, these are related by a formula which you can derive if you really want to. I can go through the derivation here. But essentially, you find that, in general, or you find that this is equal to minus b, which is, in this case is minus 1 over 1. And this is equal to, well, just minus 12 over 1, you can see. And this is generally related to essentially minus b over a and c over a for a quadratic function. And like I said, I can go through this derivation if you want. If not, I'll just proceed to show you essentially the general form. No? Okay, then the general form is simply this. If you have this polynomial, AR equals 0, then the sum of the roots, or sorry, so if you have a polynomial p of x here, then the sum of the roots is the sum of let's say the roots are some x1 x sub I, so then all of them is sorry, getting my notation mixed up, is equal to minus a n minus 1 over a n. Then the product, so I'm going to use pi notation here, is equal to minus 1 to the n. Actually, I guess I should put n's here. A0 over an, and that's it. Again, I can go through the derivation. It's not particularly fascinating. It's really just a lot of expansion and then factoring and then group collection. Thrilling stuff, I know. So otherwise, these you need to remember. They do come up on tests very frequently. Something that they will ask you, they'll ask you is, given a certain quadratic has the roots, as alpha beta, which are the roots, is equal to some value k, and alpha plus beta is equal to some value c. They generally ask, okay, what's the value of alpha plus beta, alpha squared plus beta squared, and this you need to, or they'll give you some quadratic, for example, just ax squared plus bx plus c, and they'll ask you what alpha plus beta squared, what alpha and beta are the roots, and you need to be able to factorize, basically show that this holds true, and then find alpha and beta, and then plug that in and find it. It's yeah, that's essentially how you do it. Unless you guys have any specific questions, I'm just gonna kind of blast through all this kind of easy stuff. But again, remember this, you need to remember. It's not on your formula book anywhere. It's not going to be given to you. You must remember it. I don't really have any simple tricks for remembering it. I just remember it. Okay, if that's it, I'm going to move on to solving inequalities. Okay, no questions, no concerns, problems? Wonderful. Okay, so they want you to know the general, they want you to be able to solve general inequalities such as this, where you have some function g of x is greater than or equal to f of x. Now, they allow, basically they expect three different approaches. They expect an algebraic approach, a graphical approach, and a technological approach. So the algebraic is essentially where you will be given some functions. You know, let's just say this should make up one. So x squared minus 5x plus 2 is greater than or equal to x 2x plus 5, right? And in this case, what they expect you to do is essentially to just bring it all to one side. So x squared minus 7x minus 3 is greater than or equal to 0. And then in this case, what you would do is you would essentially just solve for the zeros. So you can see on this one it's an upward facing parabola. So all you need to do is solve for the 0 points, and then that will essentially tell you, okay, well, anything above that's on either side of these zeros are going to be above the x-axis, hence greater than 0. The second approach that they might give you is they might give you, for example, some plot, or they may expect you to make a plot of some function, or maybe two functions even. For example, they could give you a straight line and some kind of cubic equation, or they could just give you one equation and tell you it's greater than some constant value, etc., whatever. And you'll be expected, for example, to say that, okay, well, this cubic, or this linear is f of x, and y equals, and I guess this is y equals g of x, and they want you to find the values where these are greater. So clearly, it's this region, so you need usually these would be on nice lattice points, so you'd be able to tell, and then again on this region here. And that's essentially what they mean by graphical approaches. The final one is technological, and that's really simple. You plug it into your calculator's graphing function, and you find the points which are above, whatever. It's not rocket science. So unless anyone has any questions, concerns, problems, practice problems they want me to do, or anything, I'll give it a second. If not, then we'll move on to, I think my next bit to do is trigonometry. Yep, so no questions, concerns, problems? If you guys don't give me anything, I'm just going to move on. Okay? Solid. How do you remember the specific shapes of graphs? Okay, brilliant question. So, how I remember them is essentially memorization, but you can figure out some of them kind of by the equation. So, for example, I know what constant graphs look like. All the most of the polynomials up to about cubic, are really easy. So, a linear graph or a constant graph is just a straight line, right? There's nothing special to it. Actually, let me draw some axes so I can kind of demonstrate this a bit more visually. So, a constant function is really no problem. It's just, a flat line. There's no slope to it. There's nothing to it, right? But a linear line, again, it's going to be in one direction. It's just a straight line. Again, another straight line. Parabolas, I just kind of know the shape of. Again, for all the basically all the polynomials, I know. It actually gets a bit more complicated after a cubic, but I know that, for example, a parabola looks like that, or it could be upside down or whatever, and that's just determined by the sign of the a value. Then cubics are a bit hard. They can take a couple forms. It can be like this, where they can have 3 intercepts. There can just be one singular intercept, where you have a saddle point and an inflection point. But essentially, you still have the same idea where it starts it starts down in the negative region and goes up, or alternatively, it goes positive to negative. Just depends on the value. but they're essentially all just kind of small transformations of the same concept. So a cubic will go from negative infinity to infinity, or the other way around. Fourth order one is going to be it's similar to a parabola. It's going to stay it's going to have less of that kind of. It's going to go from negative. It's going to go from infinity to infinity, or negative infinity to infinity, negative infinity, that kind of stuff. For other functions, like for example, the other ones I think you need to know are exponential functions, or actually, easy one is trigonometric functions. Sine and cosine are easy. Those are actually the same. Just shift them a little bit. Cosine. Tangent functions. These ones you can kind of figure out from the known values. You know that at 0 they kind of go through 0, and they have this kind of they have this kind of shape to them as they approach infinity on either side. Really, how I did it was actually we did it in two ways in our math class. We were shown a bunch of functions, told to write them down and remember them. Honestly, not too bad. It's really nice when when you have an equation, you can just bam, kind of pull up a mental image of it. Okay, actually, Benito, we actually did this in the math as cell revision session near the end. It's actually really straightforward. It's part of calculus, so I guess if we want to do it again, I'll let Creative do that. Yeah. Anyways, so then exponential functions. I essentially know that that they just a normal exponential, say e to the x, never approaches. I know one thing is that it never reaches 0. It approaches 0. All the functions, all the topics that have been covered, all the SL content has been covered in the previous live stream. Right now we're just doing the HL part of the of that. So we just covered over polynomials, so polynomial division, factor theorem, etc. And we're moving on to trigonometric in just a second. After and then I'll be moving on to actually just trigonometric, and I believe that's where I stop. And Hiram takes it over. So essentially, 1 second, my live stream seems to be messing up. Yeah, okay. So essentially, I know an exponential function. I know a couple things. First of all, I know just a basic exponential function like e to the x is going to be going up. It's just going to be going from essentially all the way to the left. It's going to be starting near 0. At the y-intercept, it's going to be at 1. That's a really important point. And then after that, it's just going to keep going up, exponentially, basically. It doesn't have this asymptote, as I've kind of showed it, but, it keeps going. No, after I finish trig, you'll be taking over here. And okay, so, so you want me to show what a tan x plus b plus c? Okay, well, essentially, that's essentially, we take the tangent function. And I mean, this is kind of going back into the SO content region of graph transformations, but the AX, all it's going to do is cause a vertical shift a vertical stretch, sorry, of A. So it's just basically going to make this bit slightly elongated, right? Then you have a horizontal stretch, and actually that's going to squeeze everything, kind of actually making it look like it's stretched even more. So that's going to make it look like that essentially. Then that shift of plus c, that's going to shift it over to left by some unit c. So in the end, the function you're going to get is going to look like that or something. I guess I'll draw it slightly better. Whoops. Okay, I apparently can't do this, but this point would be c, a negative c, basically. That's just kind of something that you have to build an intuition from, or kind of practice till you get down. But that's just transformation of graphs and knowing the shape of graphs. There's a couple other tricks you can use. For example, you can look at the derivative and second derivative, find inflection points, find critical points, zeros, and then you can kind of build up a better idea. The most kind of important one is that functions that we generally work with are continuous. So you'll have smooth transitions between different points. Not always the case, but you know. Okay, so if that's the end of that, then I'm going to move on to trigonometric stuff. So I've already covered all the basic stuff, you know, what a radian is in the previous one. If you need revision on that, go back. So I'm just going to be going over the stuff which isn't on the SL syllabus, and that's mostly these kind of identities which you aren't given in SL. So let me just dig through my. Okay, here we go. So the one thing, so the things that you guys need to know is the secant, which is just, you know, 1 over cosine, and the cosecant, and that's either written as cosec or sometimes it's written as CSC, and that's just equal to 1 over sine theta. Don't get those two confused. Some people get confused because they see the co and they think, oh, it's 1 over cosine. No, it's the other way around. Then spawning off of these, you get that you get the two identities, that 1 plus the tangent squared theta is equal to the secant squared theta. This is really easy to prove. Just write out both of these. So 1 plus sine squared theta over cosine squared theta. Oops. Raise, advance this fraction by cosine squared over cosine squared. Plus sine squared theta over cosine squared theta. Anyways, and then you can just see that this top part is the Pythagoras identity. So it's just 1, meaning that this is just 1 over cosine squared theta, which is just equal to secant squared of theta. That's it. It's the same idea with the next one, which is 1 plus cotangent squared of theta is equal to cosecant theta. That's essentially it for that. One thing, or actually, I'll get to this in a second. I'll get to this after. Then the other things that aren't covered in SL are you need to know the compound angle identities and the double angle identities. You don't need to know how they're derived. If you're interested, draw two triangles stacked on top of each other, and you can see the result kind of just pops out. But you don't need to memorize them; they're in your formula book. But then you get kind of this you get this that's yeah. Actually, I'm not going to write them out because they're in your formula book. But just remember, keep in mind for the double angle identities, the 2 inside the here. So I'll write out the tangent one, for example. You would think that I don't need to say this, but that's actually not the case. This 2 here has nothing to do with this 2. If that 2 was a 4 or whatever, it doesn't change to a 4. I have seen very smart people mess that up in a hurry. Don't do that. That's a bad idea. Okay, so I guess with trigonometric, there's a couple things that you will need to know how to do. For example, you'll need to what am I thinking? You'll need to be able to, oh right, also there's the inverse function, but I'll get to those. A lot of the time where you'll be using these most is proving other trigonometric identities. So for example, they could give you, let me just find it real quick so I can give you a real example. Sorry. Basically, you'll be given a certain apologies, I can't seem to find. Oh, here we go. Yeah. So you'd be given a certain identity, like for example, show that tan of x times sine of x plus cos of x is equal to secant of x. And you'll need to do this in kind of there's a way that they want you to do this, and you'll need to use kind of all of these identities to show it. So, oh, okay. Okay. Yeah. So essentially what they want you to do is they want you to say, you know, the left-hand side here is equal to this, so tan x sine x plus cos x, and then, you know, so you'll write this out. So this one's quite simple. So here you just get sine squared x over cos x plus cos x, and then you can advance cos x by cos x. So sine squared x plus cos squared x over cos x, and then you can see again that's just Pythagoras identity. So that's 1 over cos x, which is equal to the secant of x, and there you go. And then that's equal to the right hand side. What they don't want you to do is they don't want you to be playing with this equation as if it's a whole. No, you need to look at the separate part, either the left hand side or the right hand side. The advice that my math teacher is that take the most ugly looking side, because that's usually the easier one to work with. But you always work with one side of the equation, not the other, because then that you're not proving it. I mean, it's not the way that they want you to do it, essentially. And that's about it. The only other thing that you really need to know is the inverse functions and their domains and what their graphs look like. So what their graphs look like, again, just look it up. It's not particularly fascinating, but you do need to memorize them. But you do need to know things like, for example, you do need to know their inverse functions and their domains. So, for example, the arc sine is defined over the domain. So they all have the range. Sorry, they all have the domain -1 to 1, except for the tangent, which is different. But the arc sine has a domain. Has the range of minus pi to pi. So I guess actually I should write this as. And then the arc cos is defined from 0 to pi. Oh, sorry, this should be pi over 2, sorry. Yep. Their cos is defined from 0 to pi, and then the arc tan of x is defined actually from, I believe, was it negative infinity to infinity? Or something like that, 0 to infinity? I can't remember. Yeah, look it up, it's all pretty simple stuff. Unless you guys have any questions, problems, concerns, I do actually need to head off to dinner, and Huron will be taking over. Huron, if you want to post your stream link now so that people can hop over. Yep, okay, so seeing as how nobody has any problems, questions, concerns, anything, that's done for my bits. It's all really simple, nothing particularly interesting. Very sincere apologies, but I do actually have to go. Yep, no problem. Okay, so so check the stream chat here, and we'll post a link to his, or he'll post it in MathHL or Meter Revision, whatever. He's gonna post it somewhere. He's up next. I'll see you guys.